All right, I'm back. This is the next day, next night, and I am working on the prime sieve again. I'm just going to jump into it because I spent a lot of time just rambling yesterday, and if I start, I'll just wind up talking for an hour. So I've got rake and RakeSieve, and so what I'm trying to do is prove that at any moment the RakeSieve has these two properties, right? That there, so it has a P, which is a prime number, and a C, which is the candidate for the next prime. Whatever. And there's a set R. R is, where did it go? I need a drop down over here so I could, oh, this. R is, I guess I could just click on that, right? Yeah, I can just go to it. So R is the set of natural numbers that are greater than 2, and for every prime less than some number p, so you pass in a parameter, which is a prime, any prime less than or equal to that p, that prime does not divide the number. So it's the, I call it the residue or remaining. It's all the natural numbers co-prime to primes less than p. So in a sieve, these are the numbers that have not been sifted out yet. Right? So you mark off all the primes and their multiples, and then what's left is this R set. Okay, that's prime sieve. That's the whole point. So I did this proof, which turned out to be kind of long. That the initial state. So at the initial state, you've got your initial prime is P, is a 2, and then C has to be the next prime, and like this was what it took to prove that so that 3 is in the set of numbers that are not divisible by 2, and that it is the minimal such number. And probably this will wind up being, I'll wind up having to extract this if I ever like try and generalize this to use, other, to verify other sieves. If I have time, this is turning out to be so slow and painful that I'm probably not going to be able to do it. But I had intended to take another prime sieve that somebody else had made and verify that and show that they both implement this prime sieve class. So to implement that, I have to show those two things: that if it is a sieve state, so it has these things, it has these properties. So the idea is that you have a prime, you start with a prime, you're going to give a candidate that is just a natural number that you're saying probably is prime, according to my data structures and algorithms. And here's some proof that it has certain properties, and the properties are that it's the minimal number of the set, and it's in the set, and everything else in the set is greater than or equal to it. And then then prime sieve itself supplies the proof that that's prime. So now it sends you back a proof, this HC, that says C is a prime. The C that you gave me is a prime. And so then from that, that's the next thing. So then of course next generates a new prime, and then the assertion is that the prime, or rather it generates a new candidate, but the p value has to be the thing that we just gave you. So that's the assertion here, is saying that if I prove to you that C, I give you back a proof that C is prime, now the result of next is a new sieve state, and now P should be set to the C that I just gave you, the value of C, but that is prime now. Now we know it's prime, so whatever. So it goes from a nat to a prime. Anyway, that's the idea. So this should be pretty easy to do because it's just an assignment, and you just say that, yeah, I made that assignment. You prove that you made that assignment. And then these are the ones that are tricky. So I pushed this all the way down to the structure here. I proved it for the initial case, and now I have to prove it for next. And that's the only two cases. But I have a type error. So the property I want to prove is what? So I wrote a new function in the rake class. So or even in the rake map class. It's saying that, first of all, I made this little structure, right? It says, this is the core of the problem. This is where I'm dealing with right now. A rake map is like this. So a rake, let me fold this up. A RakeSieve has a rake map with some property. Property is a function from natural numbers to a prop, right? So it's saying it's a predicate about natural numbers. So it's saying like something about the natural numbers. And so basically we're modeling a set. And I need to basically do two things here. How do I need to show, not main, I don't want main, I wanted prime sieve. I need to model this set, right? And I believe I've done that because what I have in rake, let me just hide this for a minute. What I have is, so a rake is a collection of arithmetic sequences that all have the same slope. And I have these three operations, two operations, so I guess. So greater than or equal takes a rake and returns a rake. And it strips out all the, it adjusts all the sequences, basically kind of moves the cursor forward on them kind of by adjusting their constant term so that every number returned is greater than this number n, right? So that's how we implement n is greater than or equal to 2, because we start with the basic sequence of just 0 plus 1n, right? That's every natural number. That sequence contains every natural number. And so then if we say greater than or equal to 2, that handles this part. And then now I have to handle this part. And what I have is a mapping. I actually haven't implemented this, but I know what the type should be. So what I need to do is I need to partition the all those sequences and say for every one of those sequences, once you partition it on the, well, you just chop it into pieces and in such a way that all of the multiples of the prime that you want to filter out are guaranteed to be in, like, every sequence will either have nothing but multiples of those primes or it will never contain a multiple of those primes, of that prime. And so that's how we model that set. So that operation should be able to extract every multiple of this rem should be able to extract every multiple of this number n. And so between those two things, I can build up this set by something like induction, right? But over here it's a set, and over here it's like a chain of properties almost at the moment. Sorry, I guess I shouldn't be eating my ice into a microphone. I'm chewing on ice. So it's a little tricky. I have to they're not exact matches, and I need to prove that they're equivalent. So Yeah, so I'm still kind of thinking what my strategy is, right? Because I have to kind of unify these two statements, this statement and what I have, right? It almost makes sense to not have this, like, I'm not really sure what to do. Because these aren't the same type. So what I think I'm going to do is I'm going to get it working first. Is I don't like I think I'm going to have to like prove I have to prove that these operations are the same, like that basically if a property, something like this, like I have to prove this. Ooh, what just happened? Theorem. So if P is a property, P is a proposition, not property. R props. Right? If P is a proposition, and P PR P of n is left right, if it is equivalent to n being an element of R P for some prime. Let's call it H as a property, and then HR, and then P is going to be a prime number. P is an n prime. So we say H of n is equivalent to n being an element of RP. Then if we say H and I need another prime, right? I need and let's say how about HQ? So P and Q are primes, and HQ is that, or rather, Well, so I have this thing over here. I'm trying to figure out how to phrase it. It doesn't quite fit, right? I have this thing, not here. It's in main. It's in prime gen. It's called min prime greater than. And it should take two arguments, right? N and P, both natural numbers. But well, I guess I just need these two assertions, right? I don't need that actual structure. I keep making this, I don't know if it's a mistake, but I keep trying to tie things to a structure. Right? So let's see, P greater than, let's see, how about H? HQP, where P is greater than, or Q is greater than P. And there's another one, H Q min, which is that for all natural, all some third prime now. So now some X, there's no so if X is less than Q, then not prime greater than right. Right, we want prime greater than P, right? These should be nats. So R is okay. So the hypothesis is the same as NB. I need that. Q is that Q is greater than P. Or we say PQ. P is less than Q. It just helps to have everything be kind of like less than all the time. Maybe I should swap this over here. So P is less than Q. And really just we'll do the same way over here. So if n, just some number n is less than Q, PQ, n are all natural numbers. I don't think n has to be attached. Right? In fact, you can make these. No, because we actually have to have, these are actually part of it. This is just kind of like, n is just kind of floating around. But these two are actual parameters that we're talking about. Maybe. I don't know. Let's see. Let's just worry about that in a minute. That didn't work. Yeah, okay. So we have a proposition, and the proposition is equivalent to to some n being in. Oh no, it's actually got to be nat. Well, I'm not sure. Yeah, it has to be nat to prop. Nat to prop. And then h of n is equivalent to n being an element of R. Okay. Then Q is greater than P. Because this would only work for the next prime. Because basically what I'm trying to do is increase P. Right? And if you filter out, I want to say, really it's like H0, right? Right? And this would be, you have the function lam n. No. You have two of these, right? And then right, like this function is, I want this, right? This where is it? This. So we're saying H0n is equivalent to that. And then H1, or maybe H1n is equivalent left, right. Let me say slash left, right. You say slash if? Yeah. If and only if. If H1n is equivalent to Hn, or rather H0n, and not Q, and Q does not divide N, right? Right. So I'm making an assertion about two different properties, two different propositions. or two different functions, that map, the two different predicates. This is what we call the predicate on natural numbers. Two different predicates. So if I can show that this is a map between that, H0, maybe this should be called, yeah, this is RP. Let's call this HR0. Or maybe HH0, right? Because this is about HH0, and this is HH1. The hypothesis about H1, right? H1. In other words, H1 is just adding this and term. And, right? So it's this and this. So it's this and term is what I'm curious about. That's what we're talking about here. If that's the case, then and what I want to conclude is that H1 is equivalent to n being an element of RQ. Sorry. Okay. What's going on here? Sometimes when you make comments, they don't work out right. What's going on here? N prime. Okay, so P and Q have to be N prime. P and Q have to be N prime. And N has to be a natural number. Not Q dot val divides N. Then H1 of N is equivalent to N is, right? So this is what I want to prove. This is the fact I need to have. And I'm trying to prove that I can, that doing this operation on the propositions is equivalent to doing this change on the set, right? That, like, converting one set into a narrower set. So this is what I want to show, but it's not true. It's only true if P is greater than Q and maybe I should call these P and P1. So P, P1 and Q, P1, P0 and P1. So I can see the hypotheses, how they map up to the hypothesis. P0, right? P1. Not so, and not P1 without, and not this. And here, H inc, H inc. So P0 is less than P1, strictly less than. So so we have a P1 is a greater prime now, and H min that no really what I want to say, I don't need that file. what am I trying to say? I don't need that structure. Hmin that there does not exist, not exists q and prime. Get rid of that. Such that P0 is less than Q and P and Q is less than P1. And that should be true. I believe that, right? All right. Because if I don't have this, then at every step I'm constructing like a proposition that is like, you know, the original proposition is that like right here, right? I'm constructing this lambda that is like wrapping around the older lambda and wrapping around the older and older and older and older lambda. And you get this long chain of things, and it's like a like an inductive data structure. But I don't want that, right? I just want this. I want to simplify that at every step and say that this is the same proposition. This doesn't have to be a decidable thing. Like this lambda is like an anonymous function, but you don't have to ever actually run it, right? It exists in the type system at the type level. But even so, I don't want to build this long chain. I want to model it like this, so that it's directly talking about the set I want to talk about. So basically, this says in English that if I have a, really I should put this right underneath the definition of R, right in, where is it? Prime sieve. Okay. So first we have this fundamental thing that R is greater than P. Everything in R is greater than P. Probably I could have just used. Maybe not, I don't know. When I was proving that, maybe not, I don't know. Q. Oh, so this should be P1. P1. So if I have a proposition that models R about, you know, generally about my, if you have a proposition about something in your data structure, in your sieve implementation that is equivalent, I have a predicate, right? Predicate that is equivalent to membership in R, that is equivalent to membership in R, which is what a sieve does, right? You model that set somehow. Then anding it, and then predicate P0, right? P0, then sorry, H0. R P0 and R and P1 is the next consecutive prime, then H0 and then ANDing, then the conjunction, then adding the conjunction that I'm not sure I have to give this a name. Well, but it's fine, because this is something I would have. This is a fact I would have, because you would just write this and say, well, this is equivalent, right? Like, this is a definition. If H1 is defined this way, then you're good. That adding conjunction that but it's not really about something in your sieve. Rather, if you're really more like this. This is a statement about. This is a statement about modeling you're so okay. A prime sieve implementation is going to provide some kind of bijection between RP, right? RP0 and its internal data structures. Right? You know, we want to show so whatever the sieve does to scratch off or sift out, I guess, multiples of the next prime is equivalent to the predicate, like, you know, so lambda n you know the proof of this bijection is the How do I want to say this? The expression and n and not P1 is equivalent to the expression not P1 not P1 divides n. So this theorem allows us to construct a proposition for R or predicate in RP0 in RP1 from how about a prime sieve implementation can model R of P by providing a not providing a bijection, it's providing a I mean like you implement you implement a function that is a or you implement a relationship that is a bijection between these two sets, right? So whatever your internal data structure is and this set, the set is infinite, so you can't hold the set in memory, right? You can't have that set. You can't have every natural number in memory. So you have to have some model of it, and then you show that you're accurately modeling it by providing the bijection, okay? So because you can't have the complete set, I don't know what I'm trying to say. Between RP and its internal data structure. For RakeSieve, let's just say for RakeSieve, I chose this is exposed with a proposition this is exposed by attaching a predicate to the type, the rake map to the internal data structure. This is modeled exposed to the type system by attaching a predicate to the internal data structure. Whatever the sieve does to sift out, of the next prime, right? So following theorem allows us to construct Tn by induction using predicates of this form, using at each step. Oh, that's a mouthful. I gotta find a better way to say that. Okay, but anyway, this is so R. R next. How about that? Okay, and then so what's the proof? Do I need to prove this now? Probably. Let's do it. I mean, I do need to prove it at some point. Should I prove it now? Let's do it. It's on my mind. I think it's clear in my head. Let's try and prove it. All right, so let's bring back our proof over here. All right, so we have to show that H1n so we can simplify this. So I need to modify this statement, but I can simplify it by using this. So I can say simp HH1. Right. So now we've got a simpler statement. You can see it. That's the change. And we'll also simplify HH0. This is also showing a way. This is also a means. This is also a means to define really, I was going to say we're defining an alternate definition of R in terms of Like maybe this is the simpler thing to prove. Maybe this is the more fundamental property to prove. Let's write it like this. Theorem R next. So again, copy this whole thing and I'll simplify it down to what I think it could be. I think it could be, sorry. This is what I think it could be. So, but again, only if this. Function expected, oh, I gotta say by, right? It is expecting a function because I passed it the argument, sorry. All right, so this should work, okay. And then this is now exact. Yeah, exact that. Oh, it didn't work. Mad about this argument is the n, right? 1PQ. I didn't give it a Q. But we put Q up here. Now what do we say? There we go. So the little @ sign makes it use all these implicit arguments explicitly. All right, so now, so basically, if we can prove this little statement, then we can prove it for, we can prove that these functions are equivalent, which this is a lot simpler, right? Because this, we're just proving it right about the sets themselves. Basically, if this is the next prime, this is a lot simpler to explain, right? Now we don't have to talk about functions and predicates and all that stuff. We just say if P1 is the next consecutive prime after P0, then membership, then a member of or then I guess we'd say then R of P1, let's say left, right, R of P1 is the same as R of P0 without a cap. Same as R of P0, not intersection, but like without. How do you write that? Well, you could write it like this: that RP1 is equal to every n of RP0 and R and not P1 divides R. N. Okay, so this should be easier to prove. All right, so we have to intro an n now. Unfold the definition of R, so you see all that green stuff. That's what happened there. could simplify it. And we have to prove that it's a double-sided thing, so we have to prove it both ways. So I think we say construct. Oh. I need to figure out how to get rid of that operator. Apply if intro. All right, so now we have two cases. We're the same, except now we've got an arrow pointing right and an arrow pointing left. Or rather, we swap. It's swapped. Right? Modus ponens and the reverse of modus. All right, so case MP. Sorry, case MPR. And then the proof is complete. So let's start here, and we'll say sorry. Actually, you can put this here, and then it's tells you what you have to prove at every step. So all right, so now we have an arrow pointing to the right, so we can intro this thing, and that would be called intro HN. This whole hypothesis right here. These two things. We have to say intro HN, right? Because it's a fact about N, right? We have to prove a bunch of things, so like it's two things to prove. So we can split the ands. Split ands. What's the difference between this and apply and intro? I had left and right, and this, yeah, I don't know why that. Apply and intro. In fact, I will do this up here and say all goals apply and intro. All goals intro HN and apply and intro. Because I'm gonna do that to both sides. For the NPR case as well, right? So here. Yeah, see now it's going to give us four cases. We have NPR left, NPR right, and NPR. Right. So trying to get that at this divided by n. So what is? Should have done something. Oh, okay. So it only helped to the first one. NP that did cancel NP left, right? Went from 4 goals to 3 goals. We don't need all goals then. So case NP left. That is exact HN in left. Okay. So case NP left, I have to prove this, and it's right here. So that's easy. Case NP right. I'm going to come back to this one, so because I think this might be the same somewhere else. So let's look at this side. So NPR. Why don't I have an NPR left? Did it close NPR left as well? No, I had 2 goals. I have 4 goals. NP left, NP right, NPR left. But I'm not sure what's happening here. I have 4 goals, and then after this, I have. Why is it only saying that? Sorry. Why am I'm confused here. No goal. Okay, so, but I have 2 goals here. NPR left. What happened to MP right? This user interface is confusing. We have case NPR. Is it because I put the word sorry here? MP left, MP right. Oh, does this solve NPR right? Okay, so NPR right, and NP left should be solved. So I should have 2 goals. What? 4 goals. Yeah. Okay. Now it's showing the right thing. first of all, it's like mad about me not indenting. Like I can't put it on 2 lines, I guess. So that's part of the wrong. Like it says no goals here. But if I go down, then I have 3 goals. That's what I expect to see. Then it says case MPR sorry. So if I do that, do I have 2 goals now? No. Like, I'm confused because I was expect case MP right should be sorry, okay. And then we should say case MPR left. Sorry. Right, sorry. Right? And then it should be solved, right? That's fine. But yeah, now it's behaving the way I would expect it to. Well, see, it says no goals here. That's because I'm indented, and if I unindent, then I have 1 goal. Okay, so that's reasonable. I think what was happening was something like that. Okay, so right, that's what I need to prove. And I think if I say all goals try exact this, then at least this one. Oh no, I didn't. I thought that might enter. So, okay, so we'll just do it case by case. Case MP left. Okay. This one we can simplify a little bit. I apply and intro. Now we have 2 subcases here. HN left, but we can even just say it. I think we can say French 2 less than or equal to n. What? No. Just have 2 less LE n is equal to this left. You can say this, exact this. What's wrong with that? I thought you could say that. H2n, H2n, H2n. Oh. Oh, I see. So I have to put this everywhere. I have to do this. But no, that's not the case. I would say try have. That's silly. Okay, so it's because intro HN happened in multiple places. All right, so let's see if I can do this. We always want to intro an HN and break the HN left. I see. Slightly different. This should be possible, but I don't know if anything can see it. Omega. What? Did it prove it? What's happening here? Why don't I get an error message? Why is there a squiggly line under that if I don't get an error message? Message A greater than or equal to 2. Okay. So maybe I didn't get the error message before. Or maybe I was missing something because of this. ESOP and Omega are two like this isn't right yet. Taking its time. Hmm. Alright, so ESOP broke down on that. Alright, so we can just intro P, introduce a P that is prime, P and HP. Let's say it's also less than or equal to that. And then so this is HN. We can apply HN right at H inc. Or no, we say just say have H is HN right, and then apply H at H inc. How doesn't that work? Specialize H E0. So specialize H with P0 and then apply. I think I can do this with conv at H. At HN, so say right hand side. Right hand side, and then we're going to use H ink. Specialize H ink. Oh. Yeah, I've never been able to use the conversion tactics successfully. I haven't figured out how to really use it yet. Okay, but anyway, so apply H at H ink. I can't do that. Oh, because of this. So have P0 less than or equal to P1. And that is H ink. Sorry, P0 less than or equal to P1. Exact H ink. Oh, come on. Not exact. By rel H1. Surely if you're less than or equal to, right? By nat less than of P0 is less than or equal to P1. Surely this follows from that. It's because they're n primes, right? See, now it can prove like this. This is obvious to me, but because it's in this wrapper was a mistake. Not a mistake, but like it makes things inconvenient. All right, so now we have this, and we can apply that to this HN here. My head's getting in the way there. Shoot, this is not what I wanted to prove. I wanted to prove. So way back here, I have to pass P into here. So I have to say P0 is less than P1, P is less than P0. So first I need to say, in order to do this, in order to get this, I have to say P is less than P1. So from HP and H inc, I can say have P is less than P1, P underscore 1. And I think I have to do the same thing. Let's do this. Let P0, P1, P, and P, we'll call it PV, equal P sub 0 dot val, P sub 1 dot val, and P sub 2 dot val. Can't do that? Oh, because it's not a type. Okay. Can we do this? How to open this computer in my, can't see what that says. Big heart in front of it. Let's see my user interface here. It says, I can't see what it says. How to open this project in computer, my friend, something Python code. Well, I don't know. The actual code is here. I'll show you. Okay. GitHub.com tangent storm RakeSieve. But how to implement it in a computer, you need Lean, and Lean is LeanProver at github.io. And you'd have to download this project and install it. So I don't have a way to make that easy, unfortunately. But the basic thing you can get here, and then you can actually try it online. There's like live.leanlang.org. You can play around with the basic idea. Actually, this might You would need to have a couple definitions, I guess. Basically, these. It's not really. It's not something you can really follow along with unless you go through the steps of downloading this thing. But if you just want to play around with Lean yourself, search for the natural numbers game. Game in Lean. And when you click on this, it's going to take you to another page where you can you go to the Lean 4 version, and then you get like an interactive tutorial where you can play this. You can like learn how to use this stuff. It's really neat. So it's just Lean Game Server. It's called adam.math.hhu.de, whatever that is. Lean Game Server, maybe. Yeah, there we go. As for Python code, I don't know what the relationship is there. I'm not sure I understood that part of the question. Anyway, feel free to ask again if that did not answer your question. So I'm trying to figure out how to do all this in one statement. I thought you could do it like this, but maybe you just do it as a tuple. And there's no 2p, but p dot val. Okay, so now these have different names, and then we can say p0, pv is less than p1 by omega. Oh. Ring. No, you can't. Just okay. How about simp all? No, I thought maybe that would apply those. All goals. Simp p0. Can I do that? Nope. Can I do that? Nope. Can I do that? Oh no, because it's not. Do we say set? Okay, so say set p0 is equal to p0 dot val. Yeah. Set p1 is equal to p1 dot val. Set pv is equal to p dot val, right? And then can you rewrite this? Simp. Simp. Because you'd need something that says have h p0 is equal to as I'm just fooling around here. P0 is equal to P0 dot val, right? And then, can you then say equals reflection, right? And then, did that work? Yeah, that worked. I'm just seeing if I can eliminate these things. Right? That's all I'm trying to do here. So all goal is sim P, HP0. I thought maybe I could rewrite those in place. I can't. I wonder if I just need to teach ASOP, teach these things something, right? Right, so get rid of that. It follows from these two facts, HP and H ink, right? But this can't see it, and so every step I have to do this, and it would be nice if I didn't have to do this. And I'm wondering if I wonder if I could do this. Like, say, so instead of having prime, just have R prime, right? And have these be equivalent. P nat and HP nat dot prime P. Like, it doesn't even matter if R is prime or not, right? Like, why should it matter whether R is prime? It doesn't. What if I swap these real quick? Okay. Does anything break? This breaks. Do that now. Still not working. On line 132, what does it say here? We have to say .val here. Hmm. So there is something that kind of depends on this, I guess. All right, so I'll leave that. I'm just undo. And just have this thing HP at dot prime even though it's not used. So H is net. Or make this implicit or something. Oh no, because that's a. So you still have to have the hypothesis, even though it's not used. And then we would say that these are equivalent. Assert theorem R P so RP is left right equivalent to R prime P dot val and Yeah, problem. So given P and prime, n prime, then we can conclude this, that R of P is equivalent to, what's wrong with that? What is wrong with that? Argument RP has type set n. Oh, not equivalent to, is equal to. And then this can even be a sim. A simple lemma. By lemma. Again. Peace out. Unfold R prime. What am I doing? I have to prove these are the same thing. And simp. Are those the same thing? It's not quite RFL because it's eSimp. Okay. Apply intro. Equal with equal, is it equality relationship? How do I prove the two things are equal? Calculation? No, because we don't The difference is we have this p-val here, right? I actually don't know what the next step is. I don't know how to get rid of the equal sign. Ooh, that worked. Okay. No, it didn't work. Mm-mm. I'm just guessing. I have no clue how to do this. I don't have to do it. It's just, it would be nice to be able to show this, right? No. Oh, I know. So this for help tactic equal. Maybe this is a place to use conv. Okay, so conv. I'm just trying something. I don't even know if this is gonna work. Have HQ Q equals p.val. RFL have reflection, by reflection. What's wrong with that? Surely these are fine, right? I'd say maybe we try let. These are fine, right? Mm. Right, so the Q is a problem because there isn't such thing as Q. You're supposed to be able to coerce these things to a nat. That's the whole point of this. Was it supposed to be a drop-in replacement for a natural number? And I've made like my life so much more complicated because I use this thing everywhere. All right. How about this? Oh, that's not even a rule. Can I even say this? Oh, okay, so to prove set equality, I have to show that. Right, this makes sense. I wasn't even thinking that I was. All right, so there should be something called set if. So the two sets are equal if every member of the left set is a member of the right set. All right, that is what I want. So maybe before we do this, okay, expected check call GT. Okay, that's can we rewrite it? There we go. That's no. Oh, so this is on line 30, so it's not even us yet. Let's say sorry here. Okay, so now we got something here. Now we got two things to prove. I don't want all messages. I just want this message. So intro X. And then apply if intro. Now we have two cases, same thing we had before. HX. Here again, I'm down to one goal. I wouldn't expect Simpal to close the goal. Okay, but maybe it does. So if I say sorry here, am I in? That's it. So it closes one of the goals somehow. Interesting. Two goals. Yeah. So this does close the goal. Okay, so it closes one of the goals. So we only have to do. No, it has to be simp all. And then it works. Okay. So we introduce a P and HP. And then we say have P is less than or equal to P by can you do that? Yep, that works. And then ESOP should be able to figure this out. Nope. Oh, that's interesting. They're both the same. All right, so at H, how do we say split ands at HX? Oh, can't do that. Exact HX dot right. Apply HX dot right to this. At this. What's that? Raw P. Maybe we say simp this. Simp at this. How about specialize? I see. So okay, so this is not. This is all P. We have to say specialize this. Specialize this at. Specialize this with P. That doesn't work. With P. Mm-mm. Do anything? No. Oh, I need a prime. Uh, because this has to be a prime, right? But I don't have a prime. I only have prime. Well, P is okay. So So specialize this with P. But I need small case P. Okay, I see the problem. This is not what I need. I see the problem. Obtain F equals nat divide prime, divide prime, something like that. In fact, right? But I need a fact that says nat exists divide or something like that. Prime and divide. Like this. So obtain from. So this is, I need to pass in something because I didn't get what I wanted. But if I pass it in, I'll get back that there exists a P that is prime and it divides the thing. I need to give it a number. So a smallest factor of P. And so I do F and HF, right? There we go. So obtain the small. Oh, show P is not equal to 1. How do I know P is not equal to 1 from? Is this wrong? It is wrong. I'm trying to prove something that's not true. P greater than 1. So is it not P divides N? Okay, So that's what I need to prove. Because here it's p is prime. P is, and then so we know that that's not a problem. But here, so it's here to say to all natural numbers less than the prime, than p, we have to say p is greater than 1. Okay, so now but we'll say it is greater than or equal to 2. So all p, that if it's less than or equal to p and greater than or equal to 2, then okay. So now all right, so now we don't have, it didn't quite do what I wanted it to. So if again we do this, that's the same. And then on both sides, we want to intro p and get an HP, right? Yep. They're slightly different. The difference is that over here we have something with the primes. Okay. So here p is prime, and here p is a natural number, and here it is prime. So and then on the left hand side we're going to say intro HP2, right? So now we have this one, the modus ponens. Then let's prove the same thing, and then sim, that should solve, right? Oh, ESOP. Nope. In both cases, this is an and. So let's do this. All polls intro and then we'll simple at the end. If I can do it that way. Maybe I can't do it that way. First, you have to do simple. Oops. That worked. But here I wanted to say, oh, you have to do simple. And then after that, hx is an and, so have h. Delete, remove. It doesn't matter. I was trying to delete that. There's some way you can delete this. There's a tactic. Help tactic erase. Erase. Delete. Remove. There's a way to do that, but it doesn't really matter. But we have two copies of it. Oh, simple actually did that. Removes that redundant goal. All right, so now we've got hx broken up to little bite-sized pieces. So let's see what we can do here. So we say p does not divide x. What do we know about p? Well, p is less than 2, so p is actually that so x is greater than 2. Oh, so they're both greater than 2. And if p is less than p, all right, so we can apply this hp at x1, but I can't. I need a prime. I need a prime. Okay, I know how to prove it. So if P so hx1 says that a prime that no prime then P divides X. So I need a prime, no prime less than P. But the prime in scope is, but the P in scope is not a prime. However, but P is less than P. And P has a prime factor. Has a prime factor F, which is what I was trying to do here. All right, so so we say case MP, which is not P. You don't have to write this, but I just, it's easier to, I find it more readable. Let's write it out. Okay, so then we say sorry. Now, why can't I do this? Oh, because I have to prove that P is not equal to 1. Have P n equal to 1 equals by A sum. Okay, and then this. Yeah. Specialize hx1 with f. Let f prime be equal to f, and that's fine. And then we use f prime here. Have f prime is less than P by, oh, come on. Oh, f prime is not a prime. Have f n prime is equal to f, and that worked. No, because you have to prove this hf. So that proves that it's prime. And now we can use that to specialize hf that hx1. Now hx1 becomes this. have I have to show that f is less than or equal to prime. So let's say have f prime is less than or equal to p. I would just write this in case it can prove it. But how do I know this? Why would I think that's the case? Uh, it's because it divides it. Have so let's say so f is going to be less than or equal to p. Oh, lowercase p, sorry. Surely you can prove this. Oh. Yeah, let's equal to from HF, right? Equals this, right? Oh, is that wrong? Come on, it's prime. Nat what is prime greater than? So have this is not a theorem, so say F. I would say rewrite left. This is a definition, so I have to rewrite this at HF. At HF. There we go. So that was able to prove it. No? It's going really slow. I'm gonna restart the server. Alright, so now we can say this. You know, I'm this is a side quest, right? Like I didn't have to have the simplification rule. And like everything takes so long to prove that it's like I don't know. Like I thought I always think something's gonna be easy to prove and it's not. Right? But it was all stemming from the mistake that I made this in the first place. That I tied all this to the primes in the first place. And really I don't need to have these equivalent to each other. Like one side of it would have been fine. One of these two sides would. But okay, so now I think maybe this is easier. Now that I've got this, but it's not. Right, so what do I have here? At this point in the proof, I have f is greater than 0. What else do I know about f? It's prime, and it divides p. Because it divides p, I would expect that to say, I would expect something to do that for me. Some fact now to be able to prove that for me. Why do I believe it's less than or equal to p? Why do I believe this? Well, P is greater than or equal to 2. Okay. F divides P, great. Surely the fact that F divides P is this fact right here. How about we say have, instead of this, we say now. I don't know which one it is. Still no. What do I say? It just divides P, big P. I may be trying to prove something that's not true, but it looks like it's true to me, right? Surely, How can that not be true? Am I stupid? Am I if n divides m, it must be less than or equal to n. M, right? Right, so counterexample. Possible counterexample may satisfy the constraints a greater than 0, b is greater than 0, a minus b is greater than or equal to 1. Why does it say no goals when it... Okay, because it's in a red. We do induction here? Induction on M. Induction on N. What is this? Oh, I have to give it a name, right? So I give it a K and an HK, right? That's what it is, right? Where is this? 928, something's wrong. Sometimes when there's a syntax error in the file, like later down in the file, and it screws everything up. I think that's what's happening. So line 28, I think that's what's happening. Okay, so let's put sorry here. You have to say like with? Yes. No, but you gotta say induction on something, right? Using. Using K and HK. No. I read the whole thing. You can use with to provide the variable names for each constructor. No, that's not how. Okay, well, I guess that's just induction. Okay, so omega clears part 0. No. Is it? Wait. Okay. Say. Yeah. Still no. I don't think it solves this induction. Omega. Why would it? Because if you divide one thing, it doesn't mean you can divide. It doesn't make any sense. What is it telling me? False, right, of course. I'm doubting my sanity here. 3 divides 3 is true. So if if they're equal, then it's true. There has to be some fact about division. That help term LE of divid, nat LE of divide. What is that? This is what I'm saying. This is exactly what I'm saying. For all m and n of n, all we need to know is that 0 is greater than n, or n is greater than 0. Right? That's all we need. And this should turn up nat LE of DVD. This is exactly it, right? Okay, so why Why does that fail? Sorry, HM. If that explains why it failed. It's because everything divides 0. So M has to be greater than 0. Okay, so all that trouble was because I was missing the greater than 0. Lesson learned. I think, I hope. But with I have this, so now I have F, and this is P. This is a natural number. F is a natural number. You should have F is less than P. Less than or equal to P. And this should be like, surely it'll find the one right I defined right up here, right? What is different? P has to be greater than 0. Where did P come from? Oh, Q and HQ. Let's use this letter Q. Right? Just to make it clear where things are coming from. Right? Let's leave that there just in case I need that. I need that after all. It shouldn't. And then we'll say, okay, so P Q is not equal to 1 by 8 by. I might not need that anymore. I do. Okay, so It follows from the fact that this is q is greater than 2, so say rel hq2. Q is a natural number, is greater than or equal to 2. Surely it's greater than 0. Ring should be able to solve it. No, rel should be able to solve that. I don't know why rel can't solve it. Okay. ESOP. ESOP. Omega can solve. Okay. All right. So now it's a problem. This. Right, so now, okay, but that's what I did there. This. What did I pass in before? I passed in HM. Right. Q is greater than 0. So HM. That M is greater than 0. So on the right hand side. Okay. And I need to pass in one more thing, which is HF1. Wow, like I should not be so hard to prove things, but it. But I guess it's a skill issue, right? You know, I'm just not noticing things that are little glitches and whatnot. Okay, so why did I prove this? All right, so then now I can specialize hx1 at f this. So if we say is f prime, so hf no longer there, hf0. So for all p less than or equal to p, boom, now it's changed to f prime is less than p. So if I have f prime less than p, that is by trans by omega. Have f is less than or equal to p, val by omega. That works. Now ESOP can, so you have to take it apart and put it back together, like, which is why I'm doing this thing, so that I don't have to do this again. Okay, so now now we have a prime less than p. And then apply hx1 at this. And I think omega can do this. Cannot. Hmm. So not. Linearith? No. So again, have not F by omega. Oh. It's in timeout again. Well, so now we by contra HQX, right? So we say Q divides X. Have Q divides have F divides X by omega by trans, right? By trans is not a thing. By exact. There's some operation. Yeah, there we go. This is what I wanted. Divide is transitive. Now we have a contradiction. Okay, that's one side done. This was all just to like I'm fighting the battle I was trying to avoid everywhere else. But if I do it now, then and I do it once and for all here, then maybe I can. Like I should have just not used n prime here. That's okay. I don't really mind so much because this is practice, right? Like the real lesson here was not to do that in the first place, but now I'm creating a way to avoid it. You know, I thought it would be nice to have this bundle that like that bundle these two things together instead of just saying everywhere I needed it, just say I have a natural number and I have a proof that that natural number is prime. I should have done that. In fact, somebody told me that was the way they would structure things, and I didn't do it that way because I just it just didn't register. I didn't understand what they were saying. It was good advice, but he didn't he wasn't giving me advice. He was just showing me an example of how to do something, and then like I didn't understand what he meant. It just didn't even register that he was telling me something. Uh, what's wrong here? Because I changed something here, right? Put that there. This should be an unchanged file. What's changed? Oh, the space there. Now it's changed. Okay, that's what I expected. Why is it white? What does that white color mean? Oh, just that it's the active tab. Alright, so now because I just changed something in that file, undo a space, I have to restart this file. I don't have to, but because nothing actually changed. But okie doke. Okay. I think this comment applies only to this case. Let's put that here. Right? I'll say case, it should be called NPR, right? What else wrong? There we go. Okay. All right. So what's the goal here? Is it kind of the other direction? I have to prove that this implies this. Should be easier because now we're just wrapping stuff up. Like we should be working in fact. Okay, so we just do some mechanical stuff. What do we have? I see I've broken stuff later in the file because of something I changed. But this should be, assuming this is true, this is the end of the proof, so I don't need this, right? I don't need that sorry, I just need this sorry. I don't need it. But... Okay, so Q is less than P. Q is prime, not Q divides X. What do I know about X? Right, for all Q are prime, less than P. So this I should be able to apply hx1 at, actually just say simple. Does that work? Does nothing. Okay. So apply hx1 at hq. have, and then I want to introduce nat prime def less than, so that I can extract this, and then I will say q.prop. Nope, that did not work. Why is there a type error here? Check q.prop. Print q.print eval q.prop. Check q.prop. It is that it's we say rewrite. Have 2 greater than equal to less than or equal to q dot val exact. This should be this is again created by my own. The need to prove this is like unnecessary because it's only because I bundled this together. N is a, or P is an N prime. Say P dot val, whereas even P is greater than equal to N prime greater than equal to 2 I. P dot val greater than equal to I would say let A B A it's the same thing. I would say nat P dot prop, right? Nat prime P. Okay, and then we're going to say we're going to rewrite nat prime def lt at this. Okay. And then we say exact this dot left. And then we have it, now we've proven that. And then we can apply HQ at this. And then exact this. Did I use this fact here? Q is greater than Q? No, I didn't. That was insane. All this wrapping and unwrapping and all that stuff. Crazy. What did I break in this file? Oh, I was in the middle of a proof and I wanted this thing. Okay, so now I got completely forgotten I was even working on this. All right, so this is broken because the one above is broken. Instead of R, now let's just start this proof over and see if we can rebuild it. So we have line 95. Maybe we comment all this out, and we'll prove this. Rid of this for now, and we'll prove this one by sorry. Let's see what happens. So why is this all messed up? And we'll prove this one by sorry. Okay, everything syntax checks now, so now let's do it. So again, same thing, we're gonna have to intro n. I didn't even look, but right, it's because this is before all n, so we introduce n. Okay. And now instead of unfolding R, we're gonna rewrite R. What was this lemma? R simp, R prime. Right, so we rewrote R in terms of, and what happens if I just write simp? Yes, so this simplifies it for me, which is a little dangerous because it might, I don't even have to do that. That just simplifies it. So now we've simplified this and we can say, I was thinking in my head whether I could just simplify n prime directly, but no, I can't, because those two things are bundled together. I mean, it's because they have to be carried around together everywhere. You can't simplify it. Whereas if you have a structure you could take apart, like I don't think I'm gonna have this kind of problem with like this min thing, right? Like, because here this is not a unit that you have to carry around together. It's just like you get it and then you can take out the pieces you need. Whereas with n prime, it's a type, right? Like whereas here this is, well, I guess n prime is like carrying the fact that n is like something is prime through every step. So anywhere you pass it around, it's prime. Like you cannot create it if it's not prime. This kind of has the same feature, but when you get the value, you can take the value p out of it, and you can use it as a natural number. And you can kind of do that. Like you wouldn't just pass this whole structure around as a value, whereas I had intended n prime to just be like exactly like it's not a subtype. N prime is a subtype of natural numbers, and this is not a subtype of natural numbers. So n prime had in my mind I had an expectation that they would be almost interchangeable, and they are not. The what's called the Liskov substitution principle does not apply to these things. Right, so we can apply that or shrink that down. All right, so now let's do this. So rather than unfold an R, we just do simp. Okay. We still have an equality, so or an if. So we'll do the apply if intro, same as before, same logic as before, because it's the same statement, except now instead of something in terms of n prime, instead of this rp, we have r prime p val r prime. That's what I want to see. We could unfold r prime, and then we had like now we don't have to know what r prime is. We have the whole thing. I like that. All right, so now we have the intro, and then so we do so in all goals we're going to introduce. We only have one goal. Oh, but I closed one of them with sorry. Right, so all goals we're going to introduce. They're both n as an element. We should simp again. Simp all. Yeah, that does quite a bit. All that element and stuff. Yeah. All right, so now I can't do that yet. All right, so we're going to introduce H. Simp is simpler than that. Okay, so simp apply if intro. Oops. All right, so now we had two properties, and then so now before I had an and an or. I don't have an MP left anymore. I've diverged a little bit from my previous path. I'm trying to see if there's a way I could simplify this before I like so the next thing I'm going to do is break. Hang on. So yeah, it's weird. Okay, so yeah, so this is the left side, and then this is the whole thing is the right side. So this is the like central thing is this if. We apply that if intro, but yeah, I think that's all we can do. Now we have two goals. We can on both sides. I think this line is something I deleted. we say all goals intro n and hn. Oh, sorry, intro hn, right? It's the hypothesis. Or it's called H. And then yeah, so here we have a fact about so just to recap, we're saying that we have this, that n is an element of p0 of R of p0, and p1 is not does not divide n, and p1 is the next prime after n0. Then this n is not equal to n. Sorry, p does not divide n. P1 does not divide n. Then n is an L. Basically, if you have a set and it's the set that basically if it's the next, basically if a number is in the set of like R of p0, so all the numbers that remain after you in the prime sieve after you've crossed off all the primes up to p0, and p1 is the next prime, and this is a statement about the things that you are now going to cross off, right? This is a description of the this is basically saying that this is a statement. This corresponds to the idea that at each time you identify the next prime in a sieve, you cross out all its multiples. You sift out all its multiples. Okay. I don't know. All right, anyway. All right, so we're proving an equivalence between these two things. I should put them in parentheses. And this, just to make it clear, more readable. Okay, so this statement and that statement are and so we have to prove both sides, if and only if. And so on each side we have, so on one side we have this implies this, and on the other we have this implies this. All right, so case MP, that's modus ponens, and we'll do this, and then oops, case MPR, and then that completes the proof. Okay, so MP left. So before we had HN left. So here we do want to introduce an HN, and here we have so on this side we're going to introduce HN. Intro, we'll call this something about HQ. Oh, I see. So we have to split it. So intro. Split hands. All right, so we have to apply these in intro. Do that on both sides? Yes, we can. All right, so now we have the left and right, left and right. So now we say case MP. It should be MP left, right? Case MP right. Case MPR, the reverse, left. And so we do this and this, and then boom. And now we're solved. Okay, so exact HN left left. Do I have an HN? No, okay. Right, so what was HN? Maybe this is HN. HN. Right, so this is HN left, left. Same. Oh, exact. HN left. All right, so that is the same. And here I proved it was sorry, so I said I skipped that one. So MP rate, what do we have? Well, I just want to get all this stuff out of the comments and just make sure it's working again. So an NPR left. Is it still an and? Let's see. What does it say? Yeah, I think. Yeah, so we have an and a for all. So we'll say and intro, say apply and intro, and we'll call it H1, H2. No. But these are two goals. So we'll say apply and intro, and then we have to solve both sides. Case left, case right. And again, this is HN left, left. Exact, HN left, left. HN left. Case right. Or we can just try case off. So again, that wipes out this. So I'm just going to write that as this. Instead of hn left, I'm just write simple. And then case rate we have here. Now we have to exact hn left, same thing. And again, yeah, exactly here, we're going to intro p and hp, except now they're called q. Right, so right, intro q and hq. And now we want to get all that stuff, I think, goes away. But some of it goes away. I'm going to put all of these. Okay, first of all, let's call P and HP. And I'm going to put a note to myself to rename P to Q. But I'm just going to put it here so that I can put this code back in and it'll all, I don't have to change every line. Uncomment it. All right, so P is less than P1. What does that mean? You know, I still have n primes and crap. I'm gonna say these are gnats. If anything breaks. Okay. Instead of Q, let's say for all Q, nat prime Q implies. Oh, I see. So we'll say not exists Q where nat prime Q and so H0, and we have to put it. We have to put H1 here. Okay. Intro N. We don't have to simplify it anymore because we're already talking about it. Oh, actually, let's leave that there. It shouldn't matter. Maybe we'll do it like this. Oh, I see, but we have to. But if we're doing it like this, we have to do this. We do have to do this way. P, sorry, H0, H0, H1. R prime. Alright, so we don't need the simp anymore. I did nothing. And now, unexpected token have. Oh, because we're indent, that has nothing to do with this. Alright, intro P and HP. So again, kind of back where we were like 800 hours ago. These don't exist anymore. These don't exist anymore. How do I think P0 less than P1? It's right there. What are these? I'm just kind of like mechanically doing this. I'm not to see if they work, but what is the logic here? So I want to prove that 2 less than or equal to P. Right, so we have that from HN. So we could say, oh no, I want to have that. So apply. I want to prove that this is the case. So I want to intro HP. And so I want to intro HP2 right here. HP2. Okay, so now I have those facts. Right? So I'm assuming those facts are true. And then I have to prove that this follows. Now I want to say that, all right, so the idea was to rename this to Q. Yeah. Well, 2 less than or equal to Q. Okay, so now we can just jump right to this, I think. I think maybe I can do this. Yes, I couldn't do that before. I couldn't just directly do that before. Or maybe I could, I don't know. And so now I have this. So I can treat this like a function. So apply H at H inc. Oh, why not? Well, because it's less than. So I need this. And then I say at this. Okay, now I need 2 is less than or equal to P0. And I have So maybe omega can do this now. But I can get this. I can get this information. 2 less than or equal to P0. I have to have a term like that. I have 2 is less than or equal to Q, and Q is less than or equal to P0. So I can synthesize what I want to say. So this. Really just is 0. All I'm doing is just figuring out what I need to. Right, so HQ0, P0. Just call it Q0. All right, so then hang on. I need this. I need to get it at this. So what am I doing? I needed P1. Wait, did I need any of this? I just have to prove this. So in order to do that, I need Q less than P1. Right, so have Q less than or equal to P1. What do I specifically I need? Q less than or equal to P1. For Q less than P1 and this. So so can I do that? No. Can I pass a parameter here? Yes, so I don't need this. So like without this, H becomes this for all thing. But when I pass in P0, a P0 from the fact that P0 is less than P1, then I get right. Okay. I do need to derive this, apply this. And now to get 2 less than or equal to P0, wait, hang on. Oh, I needed this. Q. Okay, so now I have this. And then apply this at HQ2. And then we're done. Oh, I'm not done. HQ2. Q2. And then we're done. We're not done. exact this HQ2, right? Yeah, and then we're done. All right, so then I didn't do either of the other two, so oh, this is done. No goals? One goal. So. Case MPR right. And that's it. And then if that's done, then there's no goals. Then the proof is complete. All right. What's MPR right? So we have to show not P1 divides N. What do we know about N? No value less than Q, not Q divides N. Well, okay, so we do the same thing, have H equals HN right Q. But I think maybe we want P1 here. And then we have P1, which was hard to prove, but now it should be easy. I bet we can just say simp now. Simp at H. Yes. We couldn't have done that before with the wrapper because of it just couldn't see it. So presumably there's a rule that maybe we could add to when things are using n prime, the n prime wrapper. Whatever. All right, so we know that this is true because anyway, we could add a simp rule to the n prime class, but you shouldn't. You have to make all these rules, and maybe that's just not. I wonder if you can say this. I'm just curious. I want to go to a Scratch file here. Can you say, or Scratch file? Can you say abbrev n prime? No. What I was going to say is, I wanted to say, is there some way you could abbreviate it? Like x is 5 and x is a nat and nat prime x, but you can't. This is not an abbreviation because you can't use the and here because this is like you can. I guess you could have a you can't pass it around like a number. There's no way you can do that because you can't have an abbreviation for like a thing be a natural number that's a value and also have it be a proposition. Like the only way you can do that is to use a subtype like I did with n prime. If I want to do that, I have to just like define so many things that make it act like a natural number. And I did define that I could coerce it to didn't I? Well, it won't let me play because it won't let me jump like that because I haven't reloaded the file. Because it thinks things might have moved or something. Now I can go. This is coerce. I don't know. That's the other way to direct. Oh, I see. Okay. All right. Well, anyway. I guess the question on my mind was whether I could provide some more, still use the syntactic sugar, but you just can't. Like a subtype carries around the fact that it's the n prime subtype of nat carries around the fact that it's prime, but it doesn't. You can't make it any shorter. You just have to implement a bunch of things to make it act like a natural number. And I haven't implemented enough of them. You have to implement a bunch of like simplification rules and what. But what do you simplify it to? Because when you bundled a value with a proposition and you need to carry around both the value and the proposition, what is there to do? So you just break them into two separate parameters, and you just carry them. You just explicitly pass them around. That seems to be the right way to do things. Or again, add a bunch of support so that these things, that the tactics can recognize these things. And I don't know enough about how to do that yet, so whatever. All right, where are we at? Well, yeah, again, so because h1 is a nat prime, we know that this is true. Didn't I have this up here? I proved it for n prime greater than or equal to 2. But we have this. This is what we want. Rewrite prime depth LT. At h. At h. And then I think omega can close. What about this? Nope. It follows because yeah, we don't even need the simp, right? And maybe we don't even need this. Nope, we need that. Okie doke, one more case. I think I'm going to call it a night after this. All right, so we've got a for all. So we intro Q again and give it a hypothesis, something about Q. If we don't, we still get the hypothesis. Oh no, now it's parameter that we have to supply. What's called HQ. All right, what am I trying to? We're trying to prove this direction at this step. This direction. And we're trying to prove this part of it, I think. I don't know. My brain is getting tired. Oh, we can just intro this. HQ2. We can introduce those things and then Q divides in. Okay, so what do we say about not Q dividing in? Right here we have something. So HN left have H equals HN left. Actually, no. I'm just going to keep trying omega at every step. So 2 is less than n, and all right. So what is n? Where did n come from? Intro n. We introduced an arbitrary n. Hmm. Let's say we'll call this HN2. Break this into pieces. HN2 and HHH and HH or tip. And so okay. Now we've got this here. So we want to say if something for all. So this is a for all Q, right? So we want to introduce a particular Q. This Q, right? And we want to say that Q is less than. We know it is Q prime? No. So how do we know that Q is greater than 2? Q is greater than 2 from this. And is it less than P0? P0 is less than P1. That's all we know. I think we have to do cases on this. I think we have to say cases on whether or not by cases Q less than or equal to P0. Right? And if it is, case pause, right? And then okay, case neg, and then we don't need this sorry anymore. Okay, so now the case positive is you have to say, I'll give it a name, HQP. How it was called HQ0, like I said, I did in the other branch, the other thing. Okay, so then we can use HQ0 at H. So use or specialize H, or can we even say simp? Yeah, that solves that. Simple. What about this one? Simp. Oh. Okay, so then see the only statement on the right where I have this here, so maybe this is not true. Or maybe I have to derive something from here. So I got, we do have a statement here that P1 does not divide in. Do I need this? No, I did not need that to make that case. What are we doing? What does it mean here for Q to divide N? Right? Q, what is Q? Q is a number that we introduced here. Right? For all, I have to prove that for all Q less than P1. It may not be true. This may not be true, but it might. It might also be that this statement right here implies that Q is prime. I think we have to prove this by contradiction. That's my gut is telling me that. I don't know if that's true or not. But by contra H Q, what we'll call this HQN. So now HQN is the idea that Q divides N. Now, what can I show from that? Q less than, oh, so Q is greater than P0. All right, we have Q is less than, or, okay. So Q is less than P1. I think the idea is that this exists. Somehow we're going to prove that this exists. Q is prime, right? Because we have the case here that Q is less than P1. That's true. P0 is less than Q. So this is to say that HQ0. So we can say rewrite let's say simp at HQ0. Yeah. So we have this. We have P0 is less than Q. We have this. So all we have to show is that nat prime is Q. That Q is a prime. All right. Why do I think Q is prime? Or we have that Q divides N. It doesn't have to be Q itself. It could be a factor. So we could have a factor here. Where do I say obtain somewhere? This. Q has a prime factor. Q equals. I have to say Q is not equal to 1. But how do I get that back? Have Q not equal 1 equals by. Okay, so that's true. I don't even have to know why it's true. But I am curious, why is it true? Because Q is greater than or equal to 2. Okay. I think I'm just curious if we can inline this. So I don't have to give this. Maybe we do have to give it a name. I don't know a better way to do that. All right. Do I even need this? No. Like this. Oh, you know, this is I'm completely off topic here. I just want to see how do they return Oh. I was going to ask how you return multiple values from a function, but it's a proposition. So p prime p and p divides n. Okay, so that's what I need. So we have h, f. So we have f is prime, and hf divides n. H of f and n. Or I guess h of f and q, right? Right, that f divides q. And rather than trying to figure it out, let's see if omega can solve this now. Nope. ESOP. I don't know, like, I don't know what the, okay, ESOP is taking its time, it's going to time out. So we have to do some more thinking. What is this? So hmin. I want to prove that this does exist. So exists at hmin. Exists f at hmin. Nope. Exact. Say contradiction. Okay. So then I don't know how to get rid of this. So I got to read some. I just don't know how to disprove that. I mean, not how to disprove it. I don't know how to make. I don't know how to refer to this thing. I have a thing that says this does not exist, but it does exist. So how about apply exists There's nothing coming up. How about not intro at hmin? Can I do that? I specialize hmin. Specialize or f at hmin. I'm going to look at the cheat sheet here. I have it somewhere. I have something called a cheat. Just looking at tabs. I got a bunch of tabs open. 20 tabs. Report cases. Cases hmin, but it's not that. It's this cases hmin with xhx. This is for a not exist. Oh, maybe we say absurd hmin. Absurd hmin. Yeah. Cases this. No. Wait, hang on. Yes, this is what we do. We say that that's absurd, and now we have to prove that this exists, and we're going to say use f. And so now we have to prove all these things, and these are all true, I believe. And so we say, I should be able to find them. Nope. Okay, they're not true. Not prime f. P0 is less than f. Oh, okay, so have P0, sorry, P0 less than f equals ring, I ring, omega, I. Something about this. we have to say q is not 0, right? And then we can use that thing that I spent like forever trying to find. Right? And then we could say by exact. No, it has to be less than or equal to. By exact, and what is it? Oh, this must be true before, but okay, it found it. No, it didn't find it. No, sorry. Is it F? Wait, hang on. P0 is less than F by what? I'm screwing something up. First of all, let's simplify this. Simp all. Yeah, so it found some of those things. And now it has to find that P0, what did it go? So it just removed the first one. It removed a bunch of things. I really can just simplify the first one. Oh, no. P0 is less than F. How do I prove that? I was going to say if... Maybe I don't need this. I did that so that I could say that P0 is less than F because F divides Q. Well, let's say have F is less than or equal to Q. That's the exact one. That's the one that I... LE of divide, and it's this by exact has to be greater than 0. 0 greater than Q by omega of this. Okay, so now that first, I expect to have F less than or equal to Q prop. What? What I'm trying to prove. Oh, this whole thing has this type, and so I need to say F divides Q. So HFQ. Then we have that. Now that I have this, now I should be able to say omega. Make some progress now. I still got to prove the... Okay, so F... If F is less than Q, okay, so F is less than or equal to Q, and Q is less than or equal to P1, so F is less than or equal to P1. And we know that they're not the same because of this. Q divides N, but P1 does not divide N. So have Q is not equal to P1 by, oh, yeah, okay, that worked. So if Q is not equal to P1, then we have Q is less than P1. Have Q is less than P1 by omega. Yeah. Can we get rid of that? Nope. Okay, so you need both those facts. And now we should be able to show have F is less than P1 by omega. And now what about P? So that's, we have nat prime F. We have F is less than P1. What about P0 is less than F? P0 is less than Q. F is less than or equal to Q. That doesn't help us, does it? Can I prove this? Just automatically have F rather than hunt for a proof? F is, what do I need? F. Yeah. I'm trying to copy something over here, and it's like P0 is less than F. Have P0 is less than F equals by omega. Nope. Right, so I don't have any way to say that that's true. What do I know about P0? P0 is less than Q. P0 is less than P1. Well, no, P0 is less than Q. What does that tell us? Like, this is so far removed from this statement about this that I don't even know what I'm trying to prove here. But I think this is true. I think I can derive this. Like, my hunch is, like, I believe this statement is true. I could be wrong. Does not exist a prime such that this is true, so that nat prime Q and P0 is less than Q and Q is less than P1, right? Q is greater than P0. So why do I need this? I want to say that there's a prime in between these two. So prime is greater than P0. It's interesting that H min is still here. I would expect H min to go away or something. What does this tell me? So it is a prime. F is prime, right? There does not exist a prime where, right, this says this doesn't exist. Maybe that's exactly what maybe that's exactly the idea. So what happened when I tried absurd H min? Oh, I see. So I am in the middle of proving a contradiction here, right? And I'm trying to prove false. So the way I'm proving false is I say that H min is absurd. Therefore, I'm going to now prove that this exists. But that doesn't seem right. Doesn't seem right. Given a proof of P, wait, given a proof of this, P, so P is true. So H is says, but then I say this true thing is absurd and changes the goal. Yeah, I think I'm still trying to prove a contradiction here. Is there like is there a stack of like goals that I'm doing? No? I'm not seeing the user interface isn't showing me this, but I'm still trying to prove something is I'm still trying to get to false, right? Like if I say sorry here, what happens? Okay. Let's do this. So we'll say absurd H min use F, and then we'll do do split hands. I've never gotten this show thing to work. Show is supposed to say finds the first goal whose target unifies with T. And replaces the target. So show HF prime. Three goals, that splits one of them. Okay, so hey, it doesn't really matter. So the first one is temp HF1. Show P from HP. I have never won, but I don't have a function that does it, so maybe that's. I almost don't believe that that example works. But if it does work, I don't understand why it works. I lost my. Of this variable. I just do not understand this yet. I'm missing something like basic about this. Like clearly this is inside of a function. So this is okay, well anyway that's clearly this is not what I'm supposed to be doing. Yeah, I think you can choose a goal, and I don't even know what I'm doing. I'm just trying to organize this, I guess. I don't know how you say this. You don't have to give it a name, but it gets the middle goal. I don't. I guess one way I could organize it is do this. So we could say have nat prime f equals, that's just this. That's this hypothesis. This, and this. I'm just trying to like express this cleanly, right? I, oh, this is my third case. That's why I can't prove it, because they're in the wrong order, right? Or they're not in the order that I'm proving them. So this one would be sorry. And then this one works, right? Maybe that's why I couldn't do this, right? That's why just simple indentation didn't work. Okay, I get it now. It's because I was proving the wrong thing. Right, so now this one is what? This one is when I have to prove that P0 is less than F. Well, this is where we have the contradiction. So it's P0 is less than, by contra, P0 F. Let's call HF0. I even say F is less than or equal to P0. You can't say what the type is. We can say sim HF. So then well, okay, we know that we know that Q less than or equal to Okay, that works. I have that from this. Right, so now I can write that. And I have two less than or equal of f equals something about the definition of exact nat prime. No, I don't know how to do that. Nat prime def LT and just I have this somewhere. But I can't get at this unless 2 is less than n. I don't have any facts about n. I have that q divides n. And q is greater than or equal to 2. So have n greater than or equal to 2. Have 2 n equals by omega. So okay, you can figure that out. So then that hn. I still never quite get this to work. Left hand side. Left. So I don't. I need like a maybe I gotta work through the examples there. Oh. Hmm. I don't know what I'm expecting to happen at hn there. Yeah, I don't need this. I need that. I just bring this into like a hn left right. What did that get me? That got me that F does not divide N. But Q divides N and N divide so Q divides N and F divides Q. So by some trans factor, yeah. And now we have a contradiction. Wow. Okay. Boom, boom, boom. Contradiction. And that's what we set out to prove. I mean, it wants me to prove this now, right? And that's it. Is this working now? No. Because this is still in terms of R, right? And I think I'm going to get rid of this. So we're going to say these are UN, these are nat. Because this is something I'm making up brand new. And then these are both nats props. And then we have two n's here. We're going to get rid of P1. And we're going to get, we're going to have a same thing we did before a minute ago. Whoops. H0. Oops. Oh, I guess we need HP0 and HQ0. No, wait, what? HP0 and HP1, right? And HP0 would be the proof that nat prime of P0. And HP1 would be the proof that okay. So rather, yeah. And then so I never use Q. I have to provide the proofs that these are prime. So we say H or HP0, HP1, and H min is what? Get rid of Q here, get rid of this here. And this is it. Proof is complete, right? Yeah. So basically by showing that these two sets were the same, or the R and R prime are the same. Is that what we proved? No. Way up here we proved that R and R prime are the same. But down here we proved that in terms of R prime, that if you have a proposition that something is in R prime, and you also have the proposition. Wait, where did it go? So right. So you have the proposition that right. So given these conditions, then if n is a member of R prime of R of P0, and it's not divisible by P1, and P1 is the next prime after, it says P1 is the next prime after P0. Yeah, P1 is next after, then these two conditions are what define P1. And so then, yeah, okay, this is all good. I'm very surprised this took so much time to put together. But I'm glad it's true, right? And then now we can do the same thing, and we can do it in terms of what propositions? Like what changed here? So this is just a fact, and then if we have propositions about those facts, so this now we have an actual proposition here. Or, sorry, predicate, meaning it maps the natural number to the proposition. And we say, okay, we're gonna basically this is the proof that I can use those, that I can use these lambdas, these predicates, and actually write a predicate that looks just like this in order to model the set R and R next. It's complicated. I was not expecting doing all this tonight. It's 5 o'clock in the morning now. Wow. But it works. Is this used anywhere? Okay. So even with this this proof, which took a big chunk of the time, even with this simplification, this is old. This is an old thing. But even with this, like this equivalence was massive. This should I be surprised that it took that much effort to prove this? I think part of it is that I put this symbol in there, and I probably only needed one of those symbols. I probably only needed the forward case. This was probably unnecessary. I have a little, I'm making a video about this for the summer, and I'm gonna put this as a note. So our next, as something I did wrong. So I think I did that wrong. And what I did wrong was putting that symbol in there because that doubled the amount of time. Although to be fair, the fact that this implies this, it didn't double it. This was this going this way was the easier case. This way was the harder case. And this is and that was the more important case was the harder case. That's where I spent most of my time. At least it looks harder because like I don't know how much time I spent on it, but like I sort of took a lot more steps to do that. Oh, this step took the I'm just trying to imagine to see where this case came from. It came from expanding unfolding R prime, right? Yeah. So the hard part was proving this, that this came from this, because here we already had n as greater than or equal to 2. So the hard part was proving that this implied this which is buried in the definition of R prime, right? This part of R prime. And it makes sense. Right, because that's what we're actually doing is we're narrowing this set, right? In fact, this is actually says something slightly different, right? Because this says there's no prime that is less than or equal to that. There's no prime. This doesn't say that. It says every number. It says no number, right? So that's part of what the problem was. These are they say they mean the exact same thing because I proved it, but they don't have. They're not making the exact same statement. And part of the reason it was hard to prove this was a little hard because I had to obtain a prime. I had to extract a prime factor. I made a mistake here. I didn't intend. I intended for these to be exactly equivalent. But it doesn't matter. Yeah, I think I would have had a much easier time tonight had I done that. Had I included the statement. Let's say I included that q is greater than or equal to 2, but I did not include the statement that q is prime. And had I done that, I think that would have changed everything. I can change this word here just to make it's easier. Right? The q rate, but yeah, I think I would have had a much easier time had I included the fact that it was prime. Actually, this is a stronger, is slightly different. A slightly different, but it's just funny because one of the very first proofs I did was to show that these two things are equivalent somewhere. But oh well. Like, it doesn't matter. Right? If you cross out all the multiples of the primes, you're crossing out all the multiples of every number less than p. That's the point. But it doesn't really matter because these two are equivalent. In fact, the thing is called no prime factors implies no factors. That the thing is prime. If you have no prime factors other than yourself, you're a prime number. But if you have no, but the way Lean defines it is that if you have no, Lean uses this definition to define prime. So this is the definition of a prime number in Lean. This right here. This says except here it would be just not exist q. Right, this obviously the fact that it's less than or equal to. So I guess if you filter it, it doesn't matter. I'm not going to try and explain this. But like, I mean, I made a whole big deal about this. I made like a whole theorem that said that a lack of prime factors less than p is the same as a lack of any factors less than other than yourself. And I should have put prime here. I forgot. I made a mistake, and I proved something that was equivalent. But it doesn't matter. It really does not matter at all. Well, it kind of matters. Does it? No, because this is what I care about. So the fact that r prime is not defined in terms of a prime number, like it takes a prime number as an argument, but it doesn't use that proof. It's that this step is only here because to make this equivalent exact, to make these exactly equivalent. The same, like R prime doesn't have to be, or neither one of these really has to be defined in terms of a prime. Whatever. But really, the more important thing is this. Like this, just kind of like, because this was a prime, because this was a nat prime, this is a nat prime. That's subtle. Like the definition is the same, but here Q is a nat because P is a nat, right? And so I lost, so even though it looks exactly the same, except for the dot val, I lost the fact that I was talking about primes over here. But these statements are equivalent anyway, because if no prime less than P divides the number, then no number at all less than P divides the number, so they're exactly equivalent. As it happens, the operation I need to do is to filter out all multiples of a prime, right? But as long as all this stuff holds, that doesn't matter. So I didn't waste my time here. I just, I didn't prove the wrong thing. I just, I proved more than I needed to. I didn't have to spend all this effort tonight. And I also didn't have to spend effort proving things in the other direction. But whatever. Maybe I'll get better at proving things by, and maybe I'll get better at deciding what to spend my time on. Yeah. Whatever. It works. Okay, so what am I gonna call this? I'm gonna say reformulated R without how about R equals R prime. How about R P equals R prime P at prime P P n prime. How about just introduce R prime? R prime, simpler. And then prove that the real important thing was R next. What else did I modify? I modified lake. Yeah, but this doesn't affect that. Right, so now, but so yeah, so the benefit of this was I have that, I can show that providing the bijection to the set, which is what those, well, there is a bijection, and there's a function that because of that bijection, I can I can prove that the rake map proves that whatever the rake map can produce the proposition. It's easier to generate the proposition than just to describe the set without the primes removed. I don't know. Maybe I'm just rambling here. Whatever. This was progress. I'm going to commit and push this, commit and push this, and then yeah, try again tomorrow. Hopefully, you know, every time I look at RakeSieve, night, I guess, 5 o'clock in the morning. Every time I look at RakeSieve, I learn something new about all this stuff. Yeah. All right. I will. Oh, something printed out some primes. Okay. Not sure why that. I guess it's processing it. All right. So what's broken here? Just this stuff. Now I should be able to make this statement because this is what I have. Yeah. I don't know. All right, I'm done. Thanks for anybody who watched this. Hope it was less painful for you than it was for me.